Every time you click a mouse, type a letter, or launch an app on your phone, it all comes down to a tiny, lightning-fast command being processed. But have you ever stopped to wonder how your computer actually thinks? Well, today we're going to peel back the layers and follow a single instruction on its incredible journey through the brain of your computer, the CPU. Let's get into it. So here's our game plan. First, we're going to properly introduce the brain of the machine. Then we'll meet the specialized team that does all the work inside. After that, we'll follow one instruction on its grand tour from start to finish. And finally, we'll see how having more cores really amps up the power. All right, part one, the brain of the machine. You can think of this as the absolute central hub for all the thinking and doing that happens inside your device. So what is this thing really? It's the Central Processing Unit, or CPU for short. This is the component that executes every single instruction, performs all the calculations, and basically manages the entire flow of data. And it's not just one single thing. It's really a team of three core components working together: the control unit, the arithmetic logic unit, and the registers. We're going to meet them all. Okay, section 2. Let's meet the processing team. And to really get a handle on this, I want you to imagine the CPU as this incredibly efficient, high-tech factory. It's like a perfectly synchronized assembly line running inside your computer. Every factory needs a boss, right? Someone calling the shots. Well, in our CPU factory, that's the control unit, the CU. This is the foreman, the director of operations, the one making sure everything happens exactly when it's supposed to. The control unit's job is to direct and coordinate everything. So think about when you hit save on a document. The control unit is what grabs that save command, figures out what it means, and then sends out the order to the hard drive saying, hey, you need to write this data now. It's the ultimate project manager telling everyone else what to do and when. So if the control unit is the foreman reading the blueprints, then the arithmetic logic unit, or ALU, is the master craftsman. This is the specialized machine on the factory floor that does all the actual number crunching and decision making. And the ALU has a very specific skill set. It handles all the math, addition, subtraction, you name it. When your spreadsheet instantly totals up a column of numbers, that's the ALU. It also handles logic. When a video game has to figure out if your health is less than 0, yep, that's the ALU making that comparison. And when it gets a result, it needs a place to jot it down for a split second. That spot is called the accumulator. It's like the ALU's personal scratch pad. Now, even a master craftsman needs a good workbench, right? That's what registers are. Think of them as tiny, ridiculously fast storage spots that hold the exact piece of information or the specific tool that's needed right this second. They're so fast because they're built right onto the CPU chip itself, so there's zero travel time to get what they need.
And here's a quick tour of that workbench. The program counter, or PC, is like the foreman's to-do list. It always knows the address of the next job. The instruction register, or IR, holds the blueprint for the job they're working on right now. The MAR and MDR are like the loading dock. One holds the address of where to get supplies, the other holds the supplies themselves. And we already met the accumulator. That's the craftsman's scratch pad for quick calculations. Every single one has a very specific critical role.
So how does everything get from the loading dock to the workbench to the craftsman? That's where buses come in. These are literally the conveyor belts of our factory. They're just communication pathways. You've got an address bus to send out the location for a part, a data bus to bring the part back, and a control bus that carries the foreman's start and stop signals. It's a whole transportation network. Okay, part 3, an instructions grand tour. So we've met the whole team, we've seen the factory floor. Now it's time for the main event. We are going to follow one single instruction as it moves through the famous fetch, decode, execute cycle. The whole thing is basically a simple 3-act story. A story that repeats itself billions of times every single second. Act 1 is fetch, which is the pickup. Act 2 is decode, the translation. And Act 3 is execute, the action. So let's start with Act 1, fetch. The foreman, our control unit, needs the next task, so it kicks off this high-speed pickup mission to go grab the next instruction from the computer's main memory. Okay, let's trace the path. First, the program counter, the to-do list, has the address of the next instruction. It hands that address over to the MR. You can think of the MR as writing that address on an envelope. That envelope gets sent out on the address bus conveyor belt. The main memory finds that address, grabs the instruction, and puts it on a different conveyor belt, the data bus, which brings it back to the MDR. The MDR opens the package and hands the instruction to the instruction register. Phew, it's arrived. And that brings us to Act 2, decode. The instruction is here, sitting in the instruction register. The problem is it's written in machine code, just ones and zeros. So now the control unit has to put on its translator hat. This is that magic moment of translation. The control unit looks at that string of ones and zeros and acts like a code breaker. It interprets the code, figures out what it's supposed to do, and determines all the steps that need to happen next. Does this mean add? Does it mean move data? This is where the plan is made. And that brings us to the grand finale, Act 3, execute. The instruction has been picked up, it's been translated, now it is time to actually do the thing. The control unit gives the green light, and the ALU gets to work, performing whatever math or logic is required. The result might get jotted down in the accumulator for a moment, or if the job's all done, it might be sent all the way back to main memory. But here's the coolest part. While all of this is happening, the program counter has already updated to point to the next instruction in line. So the second this cycle ends, the next one is ready to begin. Fetch, decode, execute, again and again and again. So that's the journey of one instruction, happening at a mind-boggling speed. But think about it. How does your computer stream music, let you browse the web, and pop up notifications all at once? Clearly, one assembly line just isn't going to cut it. You need more. And that's the difference right here. A single-core processor is our original factory with just one assembly line. It can only do one thing at a time, just really, really fast. A multi-core processor is like upgrading our factory to have multiple parallel assembly lines. Each one of those cores is its own little CPU running its own fetch, decode, execute cycle all at the same time. Today's CPUs have 8, 16, sometimes way more cores. And that's not even counting other specialized processors. Think of your graphics card, your GPU. If the CPU is a factory with a handful of super skilled, versatile assembly lines, the GPU is like a mega factory with thousands of simpler lines that are all experts at one specific task, drawing pictures on your screen. It's all about parallel processing. And look, this matters because it's what makes your entire digital life work. Having multiple cores is the reason you can have music streaming, a dozen browser tabs open, and be typing in a document without your computer just freezing up. It's what gives you the power for heavy-duty tasks like editing video or playing a beautiful, complex video game. It is the engine that drives modern multitasking. So we followed an instruction on its journey, a fundamental cycle that has been the bedrock of computing for decades. But as we stare into the future, with the massive demands of AI and the totally new paradigm of quantum computing on the horizon, you have to wonder, is the fetch, decode, execute cycle going to be around forever? Or are we on the brink of discovering a completely new way for our machines to think?